Okay, I'm back. Last time we did an overview of OSI, and this time we're going to start at the bottom of the stack, and we're going to talk about layer 1, hopefully layer 1 and 2. Hopefully we can get through that. Break it up, so hopefully it's not as long as the last one was. I thought that was going to be about a half hour, and it ended up being an hour. And if you're, as you're watching these, I'll be adding them one at a time. So you may not get to this until all these are posted, but you may get to it. Keep checking back until I get all the way done with OSI. So we've got my plan is to do layers 1 and 2, and then 3 and 4, and then 5, 6, and 7 will go very, very quick, and then I'll go back through and do an advanced on that. So I'm looking like there's going to be 3 more, really. Okay, we're looking in the chapter 6 book because the chapter 7 book sucks. We already looked at this, and so at the physical layer we're not adding any header or trailer information, so that part's pretty simple. We get down to the functions over here: manages signaling to and from physical network connections. There's not a lot at the physical layer. All right, so it's, let me switch back over, network card, which technically is going to be both of these. We'll get to that in a little bit. Wire connectors, passing bits. We could put the monkey on a scooter at this. So this is data delivery. Basically everything about that and about that delivery from point A to point B, and the IEEE specifications for that for wires and connectors, and would be throughput and cable length. All of that is going to fit here. Now, the NIC actually does sit here at the data link and the physical, and so we'll get to that in a minute. One of the things I do want to talk about on the physical, and I mentioned it in the last video, is it is the simplest and fastest. So simplest, fastest. So if we're trying to do things and we're trying to do something very fast, we want to be, again, as low in the stack as we possibly can. Now, one more thing about passing bits before we go on. One of the things about the physical areas, there's no filtering. Let's add that. No filtering. And so it doesn't make any decisions about data delivery, and it doesn't examine packets to see if there are errors. So garbage in, garbage out in this case. If there is let's say there's a packet that has a malformed header, or it doesn't have a header at all. If it doesn't have a header, it can't be delivered, because we would need layer 3 information to actually give us the address so that we could deliver it. So if it doesn't have a layer 3 header information, it's undeliverable. This layer will still pass it on. It will still, so the example that I use in class typically is of a bucket brigader, and you know, you watch an old movie, farmer's barn is on fire, and so everybody from the community comes down and they make a line between the pond and the barn, and everybody brings a bucket with them, and so you have this line of people. You have this line of people from the pond to the barn, and people are set up, and whoops, you couldn't see any of that. So the people are set up there, and if we have this as the pond and this is on fire, and so the person down here scoops up water and passes it and passes it and passes it. These are all layer 1 deliveries. Pass. So let's say we're this person in the middle. And what's your job? Your job is to take something from point A and deliver it to point B. That is a layer 1 function. So as you're passing buckets, you know, it's a full bucket of water, a full bucket of water, a full bucket of water, and then it's a half bucket of water. it's a quarter bucket of water. What do you do with it? Do you stop everything and say, hey, we have some problems? No, you just pass. You get an empty bucket. So we're assuming there is another row of people that actually are returning the buckets this way. So they're going back. So you have this chain that's going around. So my job is just to pass. So, water, empty bucket, bucket of grass, like what? But what's your job? Your job is not to filter. It's not to lay the bucket down. It's not to stop this whole thing and say, wait a second, this is not. It's just to pass. And when somebody else upstream or downstream says, what's going on? My job is just to pass the bucket. That's, we have people on the assembly line. My job is to take this and do that, and that's all I do. It's above my pay grade, and that above my pay grade actually works a lot in OSI. It usually it's unknown. Something at an OSI layer above is just unknown. It just ignores it because it doesn't even see it. But in this case, we go water, empty bucket, grass, kittens. Anything goes past. You just I don't know. That's my job is to point A to point B. This will be a funny story later, but not for the cats. Anyway, that really the job of that person right there in this bucket brigade is a layer 1 function, and so it doesn't make decisions. It just passes from one thing to the other. Now, we're going to come up to this later, and I didn't leave myself a lot of room over here for devices. But we'll have a whole section on. I'm trying to move this over. We'll have a whole section on devices that we'll go through. But a repeater is a 2-port device that is a layer 1 device. So it has connection on either side, and it either goes this way or it goes that way. So if it comes inbound, it gets the signal gets regenerated and it gets sent out this way. If it comes in the other way, it gets regenerated and sent out the other way. So a repeater is a layer 1 device that repeats and transmits a message, but it doesn't filter. And if we had a multi-port repeater, which means just something with more than 2 ports, and typically it would have 4, 5, 8, 12, 16, 24 is typically how they go. We'll say we got a 4-port here. We would call that a hub. So a multi-port repeater is a hub. So it works exactly the same. If it comes inbound on one port, it goes outbound on every other port, and it does not make any decisions. It doesn't filter. It doesn't say, hey, that bucket was empty. That packet didn't have a network header. It just sends it out. So garbage in, garbage out. It takes things in, pumps them out. All right. Then we'll come back to these because there's actually some rules that go along with these that we'll do. So right after we get done with OSI, I'll probably go on and talk about specifically about devices. Okay, let's go to the data link layer. This is weird because I'm going backwards here. Second layer, we have a frame. So this is the first definition that we have. I was looking at, God, I keep forgetting you can't see that. All right, so I'm doing this backwards. Again, where data link layer talks about frames, a structured package for moving data, blah, 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 blah. There's the frame check sequence in the CRC, which we'll talk about in a minute. There's a big section about the MAC address. There's the 2 sublayers. There's the MAC address and the OUI, and I've got a whole section. Hey, we have some notes. I have totally forgotten that we have notes. We should go back to that. Hey, let's talk about the notes for a second. The OSI model, Open Systems Interconnection Model, was created by the ISO in '84. 7 layers. We've done all that before. Physical defines the electrical, mechanical, functional specifications for the transmission of data bits between communication. Blah, 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 blah. Bucket passing. Specifications define voltage levels. For us, it's transmission distances, so cable lengths, connectors, and throughput. We get down to data link, responsible for frames. We get error notification. We said the error notification at the second layer it was damaged because we used the CRC in the frame check sequence, which we'll get to in a minute. Flow control will get to physical addressing. The MAC address is probably the most important thing that we'll have here. If we go back here, the MAC address. All right, so the MAC address is known as the physical address. Whoop. The MAC address is actually an address specifically assigned to each individual device, and we don't have that. Let me go back to, so it is 48 bits long. It is unique to that device, that NIC or that device. So every device specifically has that. It is split in half. The first 24 bits, and usually, do I have that in here? Oh, shoot, I don't have that. Usually I have another sheet that I use in class, and I forgot to pull that. So the MAC address is, wait a second, I can do this. The MAC address is usually, I'm just going to do, these are actually hexadecimal. So it's hexadecimal pairs. So actually, let me see. Let's do CMD and IP config. IP I can't see because my mic is in the way. And I'm going to do an IP config all. And I'll go back up. So here's my Ethernet connection. And this physical address right there is my MAC. Hang on. Let me change that so it's a little more legible. Let's go to 36. Okay, much better. All right. So F8B156D3AFC9. Notice how it's set up. It's got dashes in between, and these are hexadecimal pairs. It's another sidebar to talk about hex. I'm not going to do that right at the moment because I actually will have binary hex and we'll do just barely any octal, but we'll do that. We'll do that later. So I guess you could pause right now and go and look at that. Maybe, although right now that lecture doesn't exist. Trust me, we'll come back to hexadecimal. So the first three of these, F8B156, is actually called the OUI, the Organizational Unique Identifier, and that is actually defines the manufacturer, or it would be assigned to Dell or Intel. And what I can do is I'll look around. Let's look at OUI Finder. So this is Wireshark, which I'll show you at a certain point. And so we're going to do an OUI search of F8B1, and I don't have to have this capitalized, 56. And if I hit enter, find, that shows that that has been assigned to Dell. Okay, that shows that that is assigned to Dell, and I'm actually running on Dell Optiplex 9020, I think, one of the machines out of the lab that I snagged as I was walking out the door in March, that I've been using, and I've got everything set up on. So this OUI specifically is assigned, and I could probably be more specific if we did. Oh, notice it has colons here. Sometimes you'll see it as colons, sometimes you'll see it as dashes, but it will always be 6 hex pairs total. The OUI will always be 3, and they're hexadecimal, which means in hexadecimal I can do, hexadecimal goes 0 through 9, and then 0 through 9, and it actually goes, there's 16 total, but we start at 0. Ordinal counting starts at 0. I'll do this again. Cardinal counting starts at 1. We're used to cardinal counting and everything that we do in school, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But actually, in computer sense, it's ordinal, so it's 0 through 9 is how we count to 10. So everything's always offset by 1. So hexadecimal is base 16, but it's actually 0 through 15. In a single digit, I can only do 0 through 9. So 10, 11, 12, 13, 14, 15. Don't worry, I'll do this again later. B, C, D, E, and F. So I can't go higher than F. Now, one of the things that you will see on a quiz or on certification is which of the following is a valid MAC address. Well, you got to know it could have colons. Sometimes it'll have periods. It could have dashes. There'll be something that connects these, but it's going to be 2 hexadecimal characters between 0 and 9, A through F. So if you get a G or an S or an L in here, you know it's invalid. If you get 5 of them, it's invalid. If you get 7 of them, it's invalid. There's going to be 6 hex pairs separated by something, and since they're hexadecimal, they have to be 0 through F. All right. And we said the organizationally unique identifier, the OUI, is the first half, which tells me, and as I said, I could do, let's do OUI. I don't know if this is going to work. I've never done this before. Let's see if I get, that wants me to look up the whole thing. Well, let's just see. So it's Dell. Yeah, it doesn't tell me anymore. I should be able to actually drill down and find that this is a Dell model, this, or this. Okay, so it's very specific to those network cards. And sometimes it's just a vendor and a single model, or because what will happen is, so I've got 3 hexadecimal pairs here. It's 48 bits. I got 24 here. So, sometimes Dell will ask for an OUI for a specific model. Sometimes it'll ask for just one OUI and it'll keep going until it runs out, and then it'll ask for another one. So it depends on how the vendor has done that. But since it has 24 bits, that's 16 million actual addresses, 16 million specific network cards it could have. This could just be as one of 1 or 2 that Dell actually has, but at least it narrows it down. And I know that this message came from, because this would be at layer 2. If I took a message that I got from this machine and I peeled it open like an onion and I looked at layer 2, I would be able to find this MAC address, and I'd know that it came from a Dell box. So now, another sidebar. When we're talking about MAC addresses, we will in this class talk about a MAC address is an immutable address that is always attached to every packet coming outbound from this machine, and it clearly identifies the network card specifically in this machine and can't be changed. There's a thing called spoofing, which is taking this and putting in a dummy address in its place. And in this class, it can't be done. One of the first things we talk about in security class is it is always done. In fact, most of the things can actually spoof a MAC address. If you're going to do anything nefarious, you always want to spoof your MAC address because you never want to give away. By the way, it is a unique ID that identifies the network card that I have in this machine. There is no other network card on the planet that has that combination of Dell assigned OUI and manufacturer assigned specific things. So someone could trace this back to that point. In fact, when I was at grad school at Eastern long time ago, I was actually a grad assistant in the business school, and Clinton was president at the time, and someone from Eastern sent Clinton a death threat from a computer lab in Lumpkin Hall. And the next day, the Secret Service were actually in the building, and they knew the IP address it came from. That's layer 3, the network address. They knew it came from Eastern. And then they went down to layer 2 and they knew the MAC address. So they got into the labs and went around and did an inventory of all the lab machines, and they found that MAC address. So they knew that the person who sent this death threat was actually sitting in this chair. And then they interviewed all the people. I just happened to have not been in that lab at that time, so I didn't get interrogated. But everybody who got interrogated because they wanted to find out who sent this death threat. Anyway, so it's very, very specific to that. And, back then, spoofing really wasn't a thing. Today, I said it's built into almost all of the security tools that we have. And actually, your network devices will also have the ability to spoof. So your router actually can spoof everything, and we'll talk about network address translation, which is something that logically does. Basically, it hides an address. So it takes machines that are behind that address and actually substitutes its own so that you can only see one. We'll talk about NAT and PAT a lot later. Okay, so the Mac. Oh, let me have Wireshark. Let me fire up Wireshark just for a second. So this is a packet capture tool, and I have not actually run this on this machine at home, so we're not going to get anything very exciting, but whoops. Since I have so many screens. All right, so there's Wireshark. Hang on. Let me resize that so we can see the whole thing. God. My right and left monitors are portrait, so they're really tall, so that came in. All right, so there's my interface list. So this is doing a packet capture. It's just, I'm getting a lot of bad traffic there. Okay, so there's some green traffic. Now I'm on a switch, so we're not going to see out a ton. Okay, and we're seeing it in real time too. So you can see my scroll bar is getting smaller and smaller and smaller. Here, let me show you this. This is cool. Weather.com, by the way, is one of the most offensive places that you can go as far as generating traffic, because it's got all these ads. Every one of these individual ads is a different connection. We'll use this when we use Netstat too. So it's just got thousands of different connections that it's actually going to generate. All right, so I'll close that out. All right, I'm going to stop this. So you see my scroll box. No, you can't, because my head was in the way. Hang on, let me move this over. All right, you can see my scroll box here is very, very small, and we didn't capture for very long, but that's a lot of traffic. Getting a lot of black tag traffic here. All right, so these are all individual packets. So let's look at this ACK packet. So there's the frame. That's layer 2. So I can look at the layer 2 information. This is all the information that's in that layer 2 header. And then actually this Ethernet 2, this is in the layer 2 header as well. So there's the destination MAC address, and there's this source MAC address. This is actually my router. It's showing that it's IP in the trailer. So this other information is actually stuff we go through in TCP/IP class, which is pretty cool. We'll do subnetting right at the very beginning, and then we get into packet breakdowns. So we actually look at it like this in this format down here. So we're actually looking at the entire capture in hexadecimal and then going through and actually looking at, so we can see there was the OUI for my machine. So that is my MAC address right there. So that's the destination. And then we're going through and it goes across, blah, 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 blah. So we're seeing this as a hexadecimal dump in the packet capture. Wireshark just does a really good job of actually translating that for us. But in class, we actually go through and I will give you, well, the plan is that I will give you this at some point. You wouldn't get this. Yeah, you might get that ASCII too. You would get this hexadecimal dump and you would have to tell me, where is it from? What's the MAC address from and to? And that's what we were looking at. So there's the IP address information from and source and destination from and to. And then there's the layer 4. So layer 2 was the beginning, and then that's layer 3 information. There's the layer 4 information, which is actually the source and destination ports and the flags that go along with them and the checksums. So, I mean, it's kind of boring for now, but once you get into it, I think it's really fascinating to see all the breakdown and see what all these flags actually do, like this don't fragment flag, the TTL, the time to live flag. It tells what different protocols are in there. It actually is, I think it's relatively interesting. And there is a certain point during that class, and I remember when I was going through doing training classes for this, there's a certain point where you can look at this and you can just start to read it. Oh, okay, there's this destination or the source address and the destination address and the source IP and the destination IP and the source port and destination port. No, I understand what kind of packet that is. When you can look at that and know what kind of packet that is, I think that's pretty cool. Is it necessary to be a NetAdmin to do that? Not absolutely, but when you understand the component parts and pieces, and that's kind of this whole thing, when you understand the individual bricks enough, you understand how they interrelate, and when there's a problem, then you can use this as a tool and go through and go, oh, I see, we got a don't fragment. So a don't fragment says, here, this ties to earlier. Remember in the last lecture, we had the assistant had two of two envelopes, and it got down and it had to be broken up. This is flag that says do not break it up. Don't break it, and if it's too big, just drop it. So that would be one thing. We're like, why is this packet not getting through? Oh, it has a don't fragment flag. So for some reason it's been tagged with that. We need to change it so it doesn't have that, so it actually can be broken up. Or this TTL is how many routers can it actually go through. The TTL on this one is 51. Hopefully, let's say it's 5. If it's 5, we say, oh, well, that's why for some reason the TTL is set at, maybe it was set at 6 initially, and every time it goes through a router, it gets decremented by 1, so now it's at 5, and it had to go through 8 routers to get there. If it ever gets to 0, it dies and gets dropped, so that would be why. So there's a lot of things as you go through here, you can look at it and go, oh, now I see. So really, if you're going to be a help desk person, this isn't really important at all. If you're going to be a layer 2 person, when you get to be layer 3, or you are the expert on that, you're the person on your enterprise network that everybody calls when it won't work, this becomes a skill that you start using. I start going through here and looking at the packet captures, and then I say, oh, yep, that's why. That's why that didn't get, because you're just seeing the data got through to this device and then it didn't go past that device, but I don't know why. When you can peel this open and start looking at it, it actually can make a lot of sense. And I know our NetAdmin, this would be the job that would fall on him, so he would have to go through. And this is it. Wireshark helps you. Now, people say, well, I have Wireshark. I don't need to understand it. I have this argument. I've had this argument with my kids. I don't need to understand math. We can use calculators. One of the times, and this was a long time ago, but the power went out. I was at Walmart and the power went out, and I'm sure it wouldn't be allowed now, but they were adding up and doing everything with calculators at the checkouts. I'm sure today they would just shut it down because they wouldn't allow that. But I had like a $5 item and a $6 item, and it came to $11, and they added tax in, and it came to like $9.50. And I said, I think you're supposed to add the tax, not subtract the tax. And the girl who was doing it held the calculator up in my face and said, "That's what the calculator says. That's what you're paying." Okay. All right. That's not right, because it was $11 plus tax. You're actually charging me less than 11. So that's not how that works. Calculators don't lie. That's what you're paying. Okay. So if you don't understand how it all works using the calculator, and I have the same argument for subnetting. The Cisco classes typically will use subnet calculators, which is great if you understand how it works. If you understand how it works, you can use a subnetting calculator. But just like using a regular calculator, when you get a total with tax that's less than the original, you have to be able to realize that is wrong and something in your calculation has gone screwy. Same kind of thing here. Wireshark is great, but you got to know what the underlying parts and pieces are and how to use it. Otherwise, it's only partially effective. And there's some things which, it's going to tell you that, oh, this is port 80. I thought it was port 443. I thought it was HTTPS. This is actually port 80. We're blocking port 80, but we're not blocking 443. I need to go in and I need to actually allow port 80 in addition to 443. I didn't have to break the packet down actually to see that, but anyway, it's a useful tool. I like it because you can see each of the individual sections. The layer 2 is in both of these, and there's layer 3, and then there's layer 4. Oh, can we get an IP packet? There's a UDP packet. We'll talk about UDP. Oh, there's DHCP. All right. This one will be even better, because there's layer 2 or that, there's layer 3, there's layer 4, and there's 5, 6, and 7. So DHCP is actually sitting vertical on 5, 6, and 7. So we can see it sits above layer 4, which is UDP. UDP is, it's connectionless, but we talked about connection-oriented, connectionless. Normally, TCP would be there, and TCP is connection-oriented, but UDP is connectionless. So this is some type of real-time, it's a DHCP request. Is it a request? Yeah, it's a request. There's the option. Oh, it's an option request, too. It's not just a request, it's a special request. Anyway, all kinds of things. I think it's kind of interesting. And we go through each of these lines just in painstaking detail in TCP IP class. But it's pretty cool because you really understand the parts and pieces in that. So just another little ad for TCP IP class in the fall. It's Tuesday, Thursday from 3 to 4:40. It used to be a night class because Bill, our net admin, taught it, but there's a lot of detail that we go through, so I flipped it and I moved it to late afternoon, and then I moved Survey of OS, which is an easier class. It's more of a lab class, and I moved that to night. Anyway, way more than we needed to know. Okay, let's go back to this. We had the MAC address to the physical address. Let's see, what else do we have from before and our... Let's go back to here. We had data link. Oh, that was the mail room. We had the CRC, which is the cyclical. CRC is the cyclic. Sometimes you'll see cyclic. I think in this book it's cyclic. Cyclical sounds better to me, and that's what I learned originally. Cyclical redundancy, check. All right, so what is the CRC? We also have the frame check sequence. They are, I can only do one thing at a time, just a second. Frame check sequence. Okay, so the frame check sequence is actually the thing that's in the header. So that's actually, oh, wait. We can see the CRC. Hang on. So we can open this up. I can show you the screen. Again, still learning. I can show you the screen. And we know the CRC is, which section is this in? All right. We should be able to see the CRC in here. Arrival time, frame. You're probably looking at the CRC and I'm not. Why am I not finding it? It's in here. It should be in the frame. There's the capture length. Is it hiding it? There's the address. There's the source. It is IP. Frame number, frame length, capture length. The CRC should be in there. Yep. It's TCP IP, frame mark, capture length. Must be hiding it. Or I'm looking right past it. You're probably looking at it. You're shouting to yourself, there it is, there it is. Anyway, the CRC is in here. Would be able, actually, it's not the CRC. It would be the frame check sequence is actually in here. Oh, it is hidden, isn't it? Yes. It does skip over it because it doesn't need it. But it would actually be cast. Yeah, we'd have to come down in here to actually find it. Okay, sorry I did that. All right, never mind. What was I doing? There we go. Okay, so the frame check sequence is actually what shows up, and the CRC, cyclical redundancy check, is actually the algorithm or the process that does it. The best analogy that I can have for the CRC is if I had a message, whatever that message was, and I had a setup where an A is a 1 and a B is a 2 and a C is a 3, ASCII, the regular ASCII setup. Can I do that? Can I? Yes, I can do it. There's our ASCII table. So we gotta go down. Uppercase and lowercase are different. Uppercase A is a 65, and then 66 and 67. So every character actually has a value. What I would do then is I would add up all of the values of everything, and I would get a grand total. So for this whole message, I would get a 467,312. And then the CRC is what computes that, and then that value would be placed in the frame check sequence inside the header on layer 2. When it gets sent to the other side, on the receiving end, it uses their CRC to do the exact same thing, and it comes up with a total, and then it compares the total that it had on the receiving end to the one inside the frame check sequence. If they match, we know we got the whole message. If they don't match, there was some type of error. Either something got added, changed, dropped, but it's not a valid packet. And in an Ethernet setting, it would be dropped. In theory, layer 2, the mailroom on the receiving end, could communicate with the mailroom on the sending end and say, hey, there's a problem, please resend. Again, in an Ethernet environment, that doesn't happen. It just drops it. And it waits until the transport layer to actually make the re-request. But that's how that works, and that frame check sequence is actually embedded in the header. And obviously, Wireshark is not showing it to us, but I know because we'll actually go through an IP class and we'll have to pull out what the frame check sequence is. It's actually in the hexadecimal. Okay, so the CRC, if I come down here, frame check sequence, this is the error checking mechanism. And that error checking mechanism is error checking if it's damaged. Now, one of the things at layer 4 was error checking missing. The mailroom does not check to see if everything's there as far as the entire message. If there are 4 envelopes, it checks each individual envelope for damage. If there's no damage, it sends it up, and that's the transport layer's its responsibility to check and make sure that all of the envelopes are actually there. So there's a lot of things. We got flow control is going to work on those two, the transport and data link. If you ever have what two layers do something, it's always transport and data link, because there's this is faster, this is more complete and takes longer, and it's the same way. One of the other things we also have is flow control. Now, flow control is the best way to explain it is I'm on the phone with you and I'm giving you my address. You say, what's your address? And I say, well, at school it would be 5001 Lakeland Boulevard, Mattoon, Illinois 61938. Normally I'm not going to do that. I'm going to do 5001 Lakeland Boulevard. The person on the other end is going to go, okay. Mattoon, Illinois. Okay. That confirmation back says, okay, I got it. So in flow control, anytime I have data delivery going one way and then a response, received bit coming back that says, okay, that's flow control. When we have flow control, or when we're dealing with flow control, you or I have a send window, which let's say I can send this much data. Hopefully your receive window is that big. If my send window happens to be that big and your receive window is this big, this is the problem we have a lot of times in class. Especially we get into, we used to have in TCP/IP class, the way I taught TCP/IP for the first time last year, but Bill, our net admin, taught it for years and years and years. And he would have a gigantic send window, and most of the students would have a fairly small receive window. So he would just, we called it teaching by fire hose. He would just puke up all kinds of information and not ask for, does anyone have any questions? Or when he did, everyone was so terrified that they didn't understand 80% of what he just said, and they didn't want to feel stupid, so they're not going to ask, hey, could I get clarification on that? I think part of it was intimidation. He was fairly intimidating. But they would wait, and then at the end would just be like, boy, most of that I went right over my head. Now, I do, we said before, I'm looking at faces and eyes and seeing, does everybody understand? So my flow control settings are a little bit better. I'm checking back to make sure. And if my send window is too large and you're not getting it, and typically what will happen on a data delivery, and this happened on a modem, that screech at the beginning of the modem was saying, hey, what size is your send window and what kind of compression or encryption or what are all the other settings we're going to use? If I send this big amount and you don't, so I send 5001 Lakeland Boulevard, Mattoon, Illinois 61938. I'm assuming you already have my information and you're just confirming that. But if you're taking it down, that was way too fast. That send window was way too large. You would say, I'm sorry, could you start that again? I'm having to actually write that down. And then I'm going to shrink my send window significantly and say 5001. Okay, Lakeland Boulevard. Okay, so now I've shrunk that way, way down, and I'm waiting for confirmation back before I go on to the next data bump. So we actually do have, it's a minor thing, but we actually do have flow control also is at layer 4. And we don't talk too much about it. Error checking is the one that we talk about. Error checking is the one we talk about a lot because it actually occurs in both, and it's two different functions in both of those. But that's one of several different things that happens in both layer 2 and layer 4. Okay. We need to get back to my notes. We don't need that anymore. All right. So, frame ordering. Oh, wait, definition of, topologies. So topologies exist here. So bus, ring, whoop, 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 flipped over. Sorry, topologies exist here. So we had bus, ring, and star. And I guess topologies. I was pointing on the screen. I keep forgetting the things you can see and things you can't. So bus, ring, star, mesh, but mesh is almost never an answer. For us, it'd be star. Star Ethernet. Now, going along with topologies, if you have multiples, if we had a hybrid environment where we had multiple topologies, we would use a bridge, which is the device at layer 2 that looks like a repeater, and it behaves like a repeater, except it can see anything that goes on at layer 2, and so we can see the MAC address, and because of that, when it has access to the CRC and the frame check sequence, it can actually filter. So it can filter, it can do some simple filtering based on MAC, or if the packet is damaged. If it is damaged, it can drop it. So it is slower because it has that extra functionality. If we had a multi-port bridge, is a switch. So what we'll talk about basically from this point on is almost every device we're going to talk about as a switch, because early on, I mean, I can remember hubs being $20 devices, or $15 devices, 15 to 20, and and switches being $30 and $40. Today, I don't know the last time I bought a hub. The last time I bought a hub was specifically because I did not want any filtering. It was for security class, and I wanted 100% of the content to be sent to all ports. So I specifically bought a hub because of that. But today, almost everything is a switch, and actually the switch that I have in my office is I think an 8-port gigabit switch, and I probably paid $17, $20 for it, something like that. So the devices are not very expensive now, and so basically everything that we use is going to be a switch, even if it's really simple and we have a very small network. Okay, back to the screen. Topologies, we said bus ring and star, but star is going to be most of it. Error notification if it's damaged. Frame ordering. If I get multiple frames, we're sending 1 through 10, and I got 2 and 3 and 5 and 8 and 9. It will put them in that order and send them up. So whatever it has, whatever the mailroom gets, it will put things in the proper order. It may not have them all, and it's not going to wait on all of them, but whatever it gets, it's going to put in the proper order, and it's going to send them up. So when the transport layer actually receives them, the network layer really doesn't care. It's going to pass them up to the transport layer, and they're going to wait there until they all are received. But the transport layer is going to receive them. The ones that it has, it's going to receive in order. We already talked about flow control and the send and receive window, and we talked about the physical MAC, the OUI. The right-hand half is manufacturer assigned. There are 2 sublayers. This is another minor thing. There are 2 sublayers, the LLC and the media access. The MAC sublayer. Question-wise, on my quizzes, tests, and on the Net Plus, you need to know that the data link layer has 2 sublayers. They're LLC and MAC. Both of them have to do with having communication between multiple between devices over a single link, and access to the cards, so that different services and components that are talking have access to a single outbound link. You're not going to get very many questions that have to do with that, and we'll come back and we'll talk. Realistically, we're not going to add too much more to that. The LLC and MAC sublayers, and they'll pop back up that this is a MAC sublayer function, but at this point, it's not too terribly important. All right, looking at this, we see Ethernet is actually spread across. So remember, Ethernet is CSMA/CD. We haven't done the 802 model yet, but the 802.3 is actually Ethernet. So for me, in my simplified version, I would actually use all 3 of these as the same. 10 base T is going to be our regular Ethernet that we would use in Star Ethernet. There's Token Ring, and Fiber Data Distributed Interface FUDI is and that's actually a MAN or a WAN topology, so we're gonna ignore that for now. but you can see that these are sitting vertically. There are some physical layer components to it, and they all have MAC addresses assigned to them so that they would sit there. And that is essentially like our NIC, because our NIC has a physical interface that we have wires and connectors to, and it actually sits up, and our NIC has a MAC address, so it actually lives at layer 2 as well. So the NIC is one thing that actually spreads across both of those layers. We started off just talking about that it was a layer 1, but now that we know that it has a MAC, we know it has to live at layer 2. And again, a lot of these things, it's more complex than this. There are some things that would go past that, so it behaves, and sometimes it's not even sequential. We'll have some things that'll be at layer 2 and 4, but not at layer 3. So sometimes it's weird, but I try to get this as simple. We already have a lot going on here, and it's going to get way more complicated when there's way more stuff in layer 4. So we're actually going to have a lot in this chart that we're going to have to lay in there, and I'm trying to make it as simple and straightforward as we possibly can. Okay, I'm probably going to need to do a few more touch-up things on layer 2, but since I'm at 50 minutes, I'm going to call it quits here, and then we'll pick up there and add layer 3, which should go pretty quickly because we just have the IP addresses there. And then layer 4 is probably the most complex layer. 2 and 4 have a lot going on, and 4 has the most going on. So we'll actually spend more time on 4, and then 5, 6, and 7, I said, we'll spend 10 minutes on. So we'll continue on the next video.